The other type of approach for basically building graph level features is looking at the graphlets. This example here, you can see the two-edge graphlet, you can see the complete graphlet, disconnected graphlet, and a single edge graphlet. And then you can basically count these in the graph and kind of come up with some sort of aggregate features based on these. Now the problem is that counting these graphlets and their occurrences is combinatorially difficult. So one might need to resort to path-based approaches instead, meaning that things such as random walk, in which an agent kind of randomly traverses the graph and then counts the occurrences of different node labels in some sense, which could be, for example, the degree labels. The labels that are the node degrees. And these are all important and critical methods in building graph level features. The features that we have been discussing so far are sort of focused on nodes. Therefore, for tasks such as relationship prediction or quantifying relationships between the nodes, basically the task in which you have the graph, you see some of the edges and you don't see some of the edges, and those unseen edges form your test set. These features are not pretty optimal. So we go to the other option, which is the neighborhood overlap detection domain. And we look at the statistical measures of neighborhood overlap between pairs of nodes. The simplest format is basically assessing the extent to which the neighbor nodes of two nodes are shared. So one measure is basically the number of neighbors that the two nodes share, or S of U and V. So using this, you can have basically some intensity, some not normalized intensity values that are going to be forming a similarity matrix. And a common strategy is basically to assume that two nodes are connected or related when they have a good amount of neighbors shared. A nicer version of the same thing is the Sorensen index, which is something like similar to, say, for example, F1 score or that sort of formula, in terms of basically considering the two nodes. So you have the cardinality of the intersection of the neighborhoods of the two nodes at times 2 divided by the summation of the degrees of two nodes. And that basically also gives you a normalized value related to the number of common neighbors that the two nodes share. Here is an example of a graph that you could use in relation prediction classifications. For example, you can see that this is the full graph on the left, and you can see that some of the edges of the full graph are kind of labeled as unseen, so these are going to be the test edges or relationships, the existence of which one is going to predict. And that is it. So this is the type of things that we're working for in the neighborhood overlap detection features. So similar to the previously mentioned version of the similarities, you have the Salton similarity or Salton index, which is defined like this. You also have the famous Jacquard overlap, which is like this, and it's basically the cardinality of the intersection of the neighborhoods divided by the cardinality of the union of them. And there are more things on this in this resource. Now here is something interesting. Now when you have basically a node and you want to see what kind of information you could get for this node, you look at its neighbors, and one assumption that you can make, which is valid in many of the applications, is that the neighbor node that has a lower degree, meaning that it is less connected to the others, has less ways to carry its information to you, therefore it is more important. With that assumption, there's resource allocation index, which counts the inverse degrees of the common neighbors of two nodes and then uses that as a measure of similarity, which is basically defined like this. And another variant of it's Adamic adder or AA index, which is the inverse of the logarithm of the degrees. Before going to the global overlap detection, let's talk about the neighborhood overlap detection again and do a summary of basically the main formulas that we learned about. We wanted to kind of go beyond a single individual node and those representations that might not be ideal for something such as relationship detection tasks, and we discussed local overlap measures. The first thing we discussed was this measure of similarity between two nodes, which is basically the cardinality of the intersection of their neighborhoods. And we mentioned that a common strategy is to assume that this value here is proportional to the probability of the adjacency matrix in the position u and v, meaning that these two nodes being connected, or in other words, related in a relation prediction task, this being 1, is proportional to this value. And then you could basically set up a threshold and use that to get to your make your predictions. Then we talked about the fact that this version here is not very normalized, so there were other alternatives. The first one was the Sorensen measure of similarity, which is based on 2 times cardinality of u. 2 times the cardinality of the intersection of the neighborhoods, the neighborhood of u and v, divided by the sum of their degrees. So this here would serve as a way of normalizing this measure. The other one that we talked about was the Salton measure, or Salton index, which is kind of similar to Sorensen in the sense that there is a normalization factor. So we have the same denominator, and on the bottom we have the square root of du times dv. Another pretty famous one was the Jaccard index. When defined between u and v, this would equal to the cardinality of the intersection divided by the cardinality of the union. Then we talked about the fact that in a graph, a node that has fewer degrees and is connected to our node of interest is kind of presumed in many cases to be more important because it has less routes of communication to our nodes of interest. So we talked about the resource allocation index, or RA index, when defined between V1 and V2, which essentially was the inverse value of the degrees of u for every node that is both a neighbor of V1 and a neighbor of V2. So here we are considering the importance of common neighbors, meaning that if there are 2 nodes that are connected to a neighbor, and this neighbor has fewer degrees, this neighbor is more important in determining whether or not these 2 nodes are connected. Because this new node is basically considered a property that these 2 share, while a lot of other points maybe don't. Then we talked about the Adamic adder, or AA index, which was kind of pretty similar to the resource allocation index, and this was basically again defined on the common neighbors, and this time instead of the inverse of the degree, we have the inverse of the logarithm of the degree. Now let's talk about global overlap measures. The first thing to consider is basically the drawback associated with the local neighborhood approach that we just talked about. And that is the fact that it's basically basing the decisions on the similarity of the local neighborhoods of the points. And it is possible that 2 nodes have basically no local overlap in their neighborhoods, but still be members of the same community in the graph, as the book mentions. So consider, for example, the similarities based on the common neighborhoods, and it is quite possible that you have a certain problem in which there are 2 points that are not connected to a common neighbor, but for some reason, when you're associating labels with them, these labels are actually the same. Now, the first thing we discuss is the Katz index. As the book mentions, the Katz index is basically one of the most global overlap statistics. And you basically want to count the number of paths of all lengths between a pair of nodes. So basically you would define it like this. The Katz index between 2 nodes is going to be This being a power of the adjacency matrix indicating the paths of length I, it's going to be the summation of all of these. And of course, you're going to have to need a beta with 0 and 1. To kind of make this not be infinite. If you want to weigh down the longer length paths. Let's first talk about the geometric series of matrices as kind of an important lemma in considering the Katz index. Let's say that matrix X is a square matrix with real values as its elements, and lambda 1 being the largest eigenvalue of X. What we want to show is that with this assumption, this series is going to be equal to I minus X minus 1 if and only if the largest eigenvalue is less than 1 and I minus X is non-singular. To show this, first consider this Sn being 0 to n summation of xi. Now if you multiply this by x, you're going to have this series instead. Now if you this time consider Sn minus xSn, it means that you are doing this subtraction. Looking at these values, you basically have I minus xn plus 1 being that side of the equation. And on this side of the equation, what you will have is you have Sn times I minus x. So if we multiply the inverse from the right, meaning that given the assumption that we had that I minus x is non-singular, we can say that Sn is I minus xn plus 1 times I minus x inverse. And now we know that given that lambda 1, the largest eigenvalue is less than 1, we know that if we approach n to infinity, this is going to be an old zero matrix. So you're going to have S infinity, which is equal to I 0 to infinity of xi, would be equal to I times I minus x inverse, which is the I minus x inverse. Now let's go to the equation of the Katz index again. We have S Katz between u and v being equal to the paths of length 1 to infinity, with a coefficient, of course, between u and v. Now we can see that in order to get the solution for this, you can essentially consider an I as well. So you basically could add and subtract an I. And if you subtract an I, you can basically see that this new I would be starting from 0 now. So the value for the S Katz of u and v would be for this and minus I. And this new S Katz is going to be a member of R. This is the cardinality of the set of nodes, and this is going to be a full matrix of node similarity. Now let's talk about the Leicht-Holman-Newman similarity, or Electron similarity, which is a slightly more complicated twist in the Katz index, because the Katz index that we discussed before has a strong bias towards the node degrees. Therefore, the nodes that have higher degrees are going to get a slightly higher score of similarity. And to kind of deal with that, Electron similarity comes into perspective. Now, in 2006, this metric was proposed as a kind of a better way to measure this type of similarity, and this time you have the number of paths between two nodes divided by the expected number of paths between the two nodes. And this expected number of paths between the two nodes is basically computed based on something called a configuration model or a random model that basically kind of provides you with the option of drawing random graphs with the same set of degree per nodes. Now, let's say that we want to compute this value for I equals 1, meaning that the paths of length 1. Now, if you consider each node in your graph, each node is going to have the same set of degrees, so it's going to have the same degree value, and you want to randomly draw a configuration or a graph with the same set of degrees. So you have du's, so d being this being the degree of node u, you have this number of edges going out. Now if you look at these dots here that are associated with the edges going out or coming into a node, you have 2m options, m being the number of edges in your graph. And this value obviously is the summation of the degrees of the nodes, and also the number of these small dots that I put here. Now, given that the node V has dV of these nodes, you have this probability of ending up there. So by drawing random models in this format, you can say that for I equal 1, meaning that for E of AUV, you're going to get the value to be du dV divided by 2m. So we said that the likelihood of an edge between two nodes is basically proportional to the multiplication of their degrees. Now, a more complicated case happens when we consider the paths of length 2. Now, let's say you have a node V1 and you have a node V2. In order to get this, in other words, in order to compute E of A2 between V1 and V2, you need to consider all the possible third nodes you use between them. So this value here is basically going to be the summation of something over the u's, or in other words, like basically all of the nodes in your set of nodes. Now first, you have dv1 edges going out, and then you have du divided by 2m, chance of ending up at u, going to u from v1, and then afterwards, you have du minus 1 because you use one of the edges for going to u. You have du minus 1 options for going out, and then you have dv2 divided by 2m, chances of ending up at v2. Therefore, this value is going to be dv1 dv2 divided by the squared version of 2m times, this is u, du minus 1 times du for all of these values. So this is going to be that. Now, as you can see, by jumping from the paths of length 1 to length 2, we have a more complicated system. And obviously for I larger than 2, it's going to be more cumbersome to carry out the task of computing the closed form or non-closed form solutions for these expected values. Now, in the paper for the Electron Similarity, what the authors did to kind of circumvent this issue is to focus on eigenvalues and eigenvectors. They relied on the fact that the largest eigenvalue can be used to approximate the growth in the number of paths. Now, according to this, if you consider P I or Pi minus 1 be the member of this domain, in which each value is the number of length I paths between the node U and all of the other nodes, then what you're going to have for all of the other nodes is that you have this equation, and you could see that for large i's this would basically be an eigenvector, and this is going to be the eigenvector eigenvalue equation, and lambda 1 is going to be the dominant eigenvalue for this matrix A. Therefore, they could kind of work with the I equal one version of that as a kind of a baseline, and you could have du dv 2m, as we discussed before, times lambda I minus 1. And using that, they define the S, basically the LNH index between U and V to be this. One thing to note is that LNH is kind of different from the CATS index. This time, you don't only work with the number of paths between the nodes. You're looking at the expected number of paths between the nodes as well. And when you give a high value for the measure of similarity between the two nodes, you mean that the paths that you're observing is higher in count than the number of paths that you expected to see between these two nodes. So you're going to have basically the indexed value from an identity matrix plus this value. You can see that this part here can be rewritten as this. So you have 0 to infinity, or still have this coefficient beta, and you have the number of paths of length I between u and v for all of the i's from 0 to infinity. And you also have the expected value of ai between u and v. Now if you compute the solution to this matrix is going to be this, in which D is a matrix with node degrees on the diagonal.